Hello and welcome to our lab on thermal expansion. Most objects, when they're heated, will expand. And that expansion is sort of governed by this equation. So let's take a look. This says that delta L, or the amount of expansion, the change in the length of the object, is equal to some initial length times alpha. Now this is the coefficient of thermal expansion, times the change in temperature, delta T. Now one thing to note about this equation, even though the object will expand in 3 dimensions, it will expand in all its volume, this equation only deals with the expansion in 1 dimension. So this is 1-dimensional thermal expansion. So a change in length, our chosen dimension, is equal to the initial length times alpha, which in fact is the coefficient of linear thermal expansion, times a change in temperature. And so in our experiment, we've got several different types of metal here: aluminum, copper, and brass. And we're going to look at the expansion of several of these. We don't know yet what their coefficient of thermal expansion is. But the greater that coefficient, the more it's going to expand with a given change in temperature. But we're going to experimentally determine that. So we're going to have to find out what these other 3 variables are: the initial length, the change in temperature, and the change in length after it's heated. So in order to do that, we have to set up an experiment to determine those variables. Now, determining the initial length of the sample is not very hard. You'll just use a meter stick to measure the length of the rod. But there is one thing to watch out for. You see, we're not going to be measuring the expansion of the total length of the rod. There are 2 clips on here, one at this end, one at that end, and those clips we're going to insert in this apparatus. One attaches here, and as this goes in, you see that there's a micrometer in here that we're going to use to measure the change in length, and that micrometer will butt against this second clip. So the expansion of this rod, the only expansion that's going to be measured is the expansion between the clips. So when you measure its initial length, L naught, you'll only measure the length from clip to clip. Okay, so we've talked about how to figure out one of the variables, the initial length of the sample, from clip to clip. Now, the second variable that we need to start thinking about is how to measure the change in length after we heat it, from when it's cool or room temperature until it heats up. We're going to heat it up nearly to boiling water temperature. So the way that we're going to measure the expansion is by using this thermometer. This thermometer abuts very firmly to make sure it touches it firmly, this secondary clip. The first clip is fixed into this block of plastic, so it's not going to move. So all the motion will be toward the micrometer. Now when you're reading the micrometer, at room temperature, let's go ahead and set it to the 0 point. There's a dial on the side that you can loosen, and then scroll this around until the needle touches 0. Now if you notice on the micrometer, it says that the least count is 0.01 millimeters, 1/100th of a millimeter. And so we've measured L naught probably in meters, and so we'll need to make sure that L naught and delta L have the same units. So make sure that your conversions work out. Now, that's pretty precise, 1/100th of a millimeter, but you can actually do better than that, because as the needle moves out, you should be able to estimate to the nearest 1/5 of the least count as it goes across. And so divide the least count into 5 imaginary spaces, and then say, okay, it looks like my needle has moved this far, plus 1/5, 2/5, 3/5, all the way up to the next least count. So for example, if my needle moves maybe from 0 to 23, and then I look at it and think, you know, that's about a little less than halfway between 23 and 24, I'm going to call that 2/5 of the way, or 0.4, then my needle has gone 23.4. And the way I would represent that data point, if you can see here, and using the micrometer, I would say that my change in length measured by the micrometer is equal to 0.234 millimeters. Remember, because each count is a hundredth of a millimeter, so 23.4 of the least count will be 0.234 millimeters. And that has an uncertainty of plus or minus 0.002 millimeters, which means that's a fifth of a hundredth of a millimeter. So that'll be sort of how you represent that data point measured by the micrometer. Now, we've talked about how to measure the initial length, how we're going to measure the change in length, delta L, using the micrometer. And last of all, let's talk about measuring delta T, the change in temperature. Now, the way that we're going to generate delta T is with a steam generator. These samples are hollow tubes, and we're going to inject steam into them. So what we'll do is down here on the micrometer end, I'm going to insert this rubber tube that's connected to this stopper that goes to the steam generator. The steam generator I'm going to fill up over the halfway point with water. It's important that we don't let it run low or the steam generator will get too hot. We need to keep water in it. So make sure that there's water above the heating band. Now once water is in here, then we'll cap it off. This cap has two plugs, but I've got one sealed off and the other one is going to my aluminum sample. So now I turn it on, I turn it all the way up to high. But before I do that, I want to get a measure of my initial temperature, because in order to find a change in temperature, unlike with the micrometer that sort of directly measured delta L, its initial position was 0 on the micrometer, so its reading was delta L. Unlike that, our thermometer, we need a final and an initial point. So we'll turn on our thermometer, and it measures Celsius degrees to the nearest tenth of a degree. Now, in order for it to work, it has to have this thermocouple attached. If you take a look, this has a wide terminal and a narrow terminal. These two electrodes, one is wide, one is narrow. And down here, there are these corresponding openings, so one wide and one narrow. It's important that you don't get them turned around backwards. Make sure the wide one goes in the wide one, the narrow one goes in the narrow one. Once that thermocouple is attached, now we're reading around 20.4 degrees Celsius. That's our initial room temperature. Now this actually fits pretty nicely into the end of the tube, and as steam is injected into the tube will heat up, it will expand, and we can read its change in temperature using this thermometer. Last of all, I have a little watch glass that I'll use to catch the condensing steam as it exits from the tube. It'll dribble into this little watch glass. So I then turn on and up to high the steam generator, and then we wait. As steam builds up in here, it will eventually go through this into the tube. One last thing. You'll get better results if it's thermally insulated. So there's this insulator, a little foam jacket that we'll put there. Do that first of all, not after you start, because you don't want it to touch any of this hot metal. The safety precaution is here, we are working with steam, and you want to be very careful not to have your hands near it, and also wear safety goggles to protect your eyes from the steam. I'm not wearing them because I'm not really using steam right now. So with this thermally insulated jacket on the sample, steam now comes in, it heats up, it expands, and it's going to happen quickly. Read the expansion using the micrometer to get delta L. At the same time, you'll see this temperature go up. Record the high temperature that corresponds with the maximum reading of the micrometer. Sometimes the micrometer can hit a maximum reading, and then as the steam begins to condense around it, the evaporating steam can cause it to cool and retract. But you want to read that very maximum needle reading of the micrometer. And so now we have it. We have L naught, we have delta L, we have delta T. you should be able to calculate the coefficient of thermal expansion for this aluminum and compare it using percent error to a known value of the thermal linear expansion coefficient of aluminum. And you can also do that for brass and copper.